Good afternoon. So in today's lesson, I want to go over two more steady state temperature problems. This time, if we're using the cylindrical and spherical coordinates, but in very simplified assumptions. I mean, in cases in which the heat equation still depends on two variables, so that the steady state temperature still becomes a single ODE. Notice so far the steady state temperature was a simple ordinary differential equation. So this is basically another version of the same type of problem. Now, just to remind you, and I hope you have this on the formula sheet, if you use cylindrical coordinates, the Laplacian that comes as part of the heat equation in general is u rho twice, u partial rho twice, plus 1 over rho u partial rho plus 1 over rho squared u partial phi twice plus u partial z twice, right? So u in general depends on the polar radius, the polar angle, and the z coordinate, right? These are the cylindrical coordinates basically. So let's use an example in which essentially the last two terms are zero. That can be if, let's say, the temperature only depends on the radius and the time t, the time t as well, I forgot the t here, or maybe the shape of the object is in such a way that there's no z coordinate, for instance. You still have to make assumption, of course, on the temperature not being dependent on phi. So here's an example. Let's say you have an object that is between two concentric circles, so like a donut. And let's say the small radius is 1 and the big radius is 5. And let's say that the heat flows only across the radius. So it follows a radial radius path, essentially. That essentially is the excuse for having u phi 0 and uz 0. uz because, let's say, it's a flat object, there's no z coordinate, but to also make the temperature the dependence on phi 0, you assume that there is an insulation across, there's a flow of the heat just across the radius. So this type of assumption could be realistic, more or less, depending on the way the material is constructed and the nature of the material, for example, that allows heat only along the radius. Now, so in that case, then the heat equation will be ut equals some constant, and then just the portion of the Laplacian that is not zero, right? The one that still depends on the radius. So now, of course, the temperature is just depending on the radius rho and the time t. What does it mean to establish boundary conditions, and what does it mean to solve the steady state temperature? Well, boundary conditions now mean what happened at the edges of the donut. So for example, let's say the inner ring is set at temperature, let's say 10 degrees, which is another way of saying that u of 1t is equal to 10. And then the outer ring of the object, let's say that it's set at temperature 2 degrees, which means mathematically I can write this as u of 5t is equal to 2. And then again, let's assume that eventually the temperature stabilizes. If we wait long enough, let's say that u partial t is equal to 0. And it should stabilize. I mean, if I assume nothing else and everywhere else we have insulation, so there's no heat coming across, inside the object from other sources, it should stabilize at some point, and it should basically be pretty similar to the one-dimensional case. I mean, there should be some sort of temperature distribution, hotter around the outer edge and cooler toward the inner ring, basically, because of the other way around, I'm sorry. Hotter toward the inner, because the inner ring is set at 10 degrees. So it should be, the object should be hotter near the inner ring. How do we solve the equation? Well, let's set it up equal to 0. So if ut equals 0, right, eventually if t equals 0, then that means the temperature eventually just depends on the radius. And because ut is 0, that means the right hand side of the ODE should also be 0. So as a side note, just to take a little bit of a break here and catch our breath, me taking a donut and not a full disk, it's actually not that it's intentional, because you might notice there's 1 over rho there. And you may wonder what happens if in the center on rho equals 0, but we're going to postpone that discussion for later. So I'm choosing essentially now an object that doesn't deal with this type of worry of having some division to 0, basically, on that boundary point. And the way to solve it, well, we basically exploit the fact that this equation can be thought as a, so this is a second order ODE in U, but, and by the way, you could also use the prime notation at this point, because if U depends on just rho, you can even write it like this now, because it's a single variable. So it's a second order ODE. It's not the one with constant coefficients, for which you can use that, if you remember that formula from ODE, from the differential equation course with the characteristic equation, because the coefficient is not constant, the coefficient of U prime. But we can still solve it if we notice that I can actually denote by y of rho the derivative of u prime of rho. And then if I replace basically u prime with y, so keep this in mind, this substitution, this becomes a first order ODE. So u double prime, so if I call y to be u prime, then u double prime is nothing but y prime. So therefore this ODE becomes y prime plus 1 over rho times y equals 0. So this essentially becomes the first order ODE, which is separable. So this is dy d rho minus 1 over rho times y. And I can simply solve it via separation of variables, the separation of variables from ODE course. So divide by y, that's minus 1 over y dy equals 1 over rho d rho. Integrate both sides, and that gives me minus natural log of y equals natural log of rho plus some constant c. Okay, now let's see if so ln of y is all right. Yeah, so let's actually exponentiate both sides. Well, I'm gonna move the minus over first. That's like ln of rho to the negative 1 minus c. We can exponentiate both sides. On the left we have y. On the right hand side we have e to the ln of rho to the negative 1 times e to the minus c. This can be renamed another constant c. And then e with the ln cancels, so this becomes c over rho. So y of rho, which remember stands for u prime of rho, is some constant of integration over rho. And then finally we get u of rho by integrating one more time, right? So u prime of rho is c over rho. If we integrate with respect to rho both sides, then on the left side we have u of rho equals c natural log of rho plus another constant d. So the steady state temperature becomes a constant natural log of rho plus d. So notice it's kind of similar, I mean, to an extent obviously, than the steady state temperature in Cartesian coordinates. We're going to solve for the constant c and d from the boundary conditions immediately, the boundary conditions which are here. But it's worth pausing again a little bit and noticing that the phenomenon here is very similar like in Cartesian coordinates, right? So in Cartesian coordinates, you have a bar, flow of heat is from left to right. You specify the temperatures, and then the steady state temperature is just a linear equation, right? So in the Cartesian case, remember we had u of x equals mx plus n, something like that. And the only thing we changed here was just the coordinate system, right? We are here in spherical coordinates, or polar coordinates if you want. It's still kind of the same type of flow, right? From one side to another, except now the side is a circular ring. And yet, as you can see, the problem is completely different from a mathematical point of view. It's a little bit harder to solve. We still integrated twice, but now we had, we have to know how to integrate ODEs by separation of variables, and all of a sudden now the function involves natural log of rho instead of just x. So this is like a segue to what happens later in the course when, for more complicated problems, changing the coordinate systems will change completely the nature of the mathematics involved in that problem, which is the reason why we have always the need for additional tools. But now going back to this problem, let's see, u of 1 of t equals 10. Remember, now u depends on rho only, so the condition is u of 1 equals 10. And that means c times ln of 1 plus d equals 10. And then u of 5 equals 2. And that's c ln of 5 plus d equals 2. ln of 1 is 0, and then that means d equals 10. And I can plug it back into the second equation. 2 minus 10 is minus 8. So c is minus 8 over ln of 5. And finally, the steady state temperature then is going to be, let's start with d. So d is going to be 10. And then plus c ln of rho. That's minus 8 over ln of 5 times natural log of rho. And notice that indeed the temperature gets hotter as you come closer to the inner ring. If I replace ln of rho with 1, I get 10. But as rho increases from 1 to 5, the temperature becomes lower and lower because you approach the colder edge, which is the outer edge in this case. We're going to do another example on the second page, so stay tuned. All right, so take a moment to write this down. This is actually from our textbook, but the idea is to find the steady state temperature for a solid bounded by two concentric spheres. So the way to sketch them looks like circles, but keep in mind these are now spheres. So two concentric spheres. The smaller one has radius A, the outer one radius B. And then we have the inner surface identified by the radius A is kept at temperature 0 degrees. And then the outer surface R equals B is kept at temperature U naught. You already have the answer of this problem, but basically don't look at the answer too soon, just go through the process of solving it. So I want to point out that it's very important not to confuse the two equations, the one in cylindrical coordinates and the one in spherical coordinates. When you talk about spheres, you obviously use the spherical coordinates, and remember the notation we used was rho, not rho, u dependent on r, phi, and theta, and then of course the time t, the spherical coordinates. Now in the simplified version of the problem, we assume that heat again flows only along the radius, which allows us to have only the first portion of the Laplacian, the one not involving phi and theta. So basically the portion with phi and theta will be 0. Just u partial r, the distance from the center to the point is the one that matters. But in this case, the Laplacian, although it's kind of similar to the first one, to the one in cylindrical coordinates, it's not the same. It's u r twice plus 2 over r u partial r. So there's 2 over r instead of 1 over rho, like it was in the spherical, like it was in the cylindrical coordinate case. So again, because we assume that the temperature no longer depends on the temperature on the time t, then the Laplacian set it equal to 0 when you set it up for the steady state temperature becomes a single ODE in R. So U depends on R only, and then the equation to solve is U partial R twice plus 2 over R U partial R equal to 0. So there's a hint in the problem that states that this can be written as the double derivative of a product. So you could do it basically in the same manner we did it before. Like we can substitute y with u partial r, and that gives you a single ODE in y. So you can try it this way. Another way, as the problem mentions, is to notice that, or to check even, that this quantity is nothing but the second derivative with respect to r of the product r times u. So let's actually check. Let's differentiate with respect to r once. So, so the second derivative with respect to r is the first derivative. And now let's do it with respect to r once. So the product rule is 1 times u plus r times u partial r. And now again, another derivative, that's going to be ur plus another product rule, 1 times ur plus r times partial r twice. So this ends up being 2ur plus ru r twice, and that's equivalent to the steady state temperature equation. Because notice, if I look at the steady state temperature, if I multiply by r both sides, this becomes 2u partial r plus r times u partial r twice. So either you make the substitution that I mentioned here, or if you notice that you can combine this quantity into a double derivative, either way you can solve the ODE. So if you notice that it's a double derivative, all you have to do is to integrate twice r times u, right? So the steady state temperature is nothing but the second derivative of r times u, which is equal to 0. So to find u of r, we're going to integrate with respect to r once, and that'll give me the first derivative with respect to r equals the integral of 0, which is just a constant. Let's call it c. And then we integrate with respect to r one more time, and that gives me r times u equals cr plus another constant d, which we're going to solve in a minute. So basically u of r is going to be cr plus d over r, so that's going to be c plus d over r. So this is how the steady state temperature looks like in the spherical coordinates case, if you want. All right, so let's impose the boundary conditions. So the problem states that u at the lower radius, so when u of little a, that's kept at 0 degrees, so u of a is 0. That means c plus d over a is equal to 0. And u of b, the outer radius, is going to be u naught. Again, a given temperature. So that gives me c plus d over b equals u naught. So you just need to find c and d. The easiest thing is just to subtract the two. because that eliminates c. So I get d times 1 over b minus 1 over a equals u naught minus 0. Let's see if I write it here. So that's going to be d times a minus b over ab equals u naught, which means d equals a b u naught over a minus b. And then let's get c from the first equation. So c equals minus 1 over ad minus 1 over a times d and we're almost done, right? So now plug in these constants into the formula for u. So c, we can start actually with the positive one, with d. Well, no, let's start with c. Trying to look it up what the way it's given in the yeah, I think it's, yeah, let me write it down like this. So it's gonna be c minus b u naught over a minus b plus 1 over r times d. So in the answer given, usually it's given with b minus a on the bottom. So you can pull out actually minus b over a minus b, which, let's see, minus b u naught over a minus b, which can be written as b u naught over b minus a if you revert the sign. And then it's going to be 1 minus a over r. All right, so I think that's it for today. We're gonna continue, as I said, next time to discuss another important physical equation, which will spend quite a lot of time together with the heat equation, namely the weight equation. But for now, that's it for today.